Good afternoon, everyone. Am I audible to you? Is the quality of voice audible or is it's clear now? JNV, I think JNV PTA, JNV PTA has joined. So is it clear now? Okay. What is the full form of this PTA? Can you hear me out? Okay. So we will start. Bacha, what is the full form of JNV PTA? PTA stands for. Okay. Okay. So we are moving towards today's lecture. First of all, we will recall what we have studied in the previous lectures. Like we have completed two chapters. So I'm not going to discuss all those two lectures here. What I will discuss the previous lecture. In the previous lecture, what we have studied about some part of the RMS current, like some revision of RMS current. And after that, what we have studied is AC circuits. In AC circuit, one more thing which is very important that we have learned what is the concept of leading, what is the concept of lagging. If somewhere it is written as current is leading voltage, yeah, current is leading EMF, what does it mean? So these were the basic things. Like if I draw a graph in front of you, I'm not an expert in such kind of drawings. Like suppose this is voltage and I'm drawing another graph. This is for current. This is for current. Can you tell me out of these two graphs, which is leading and which is lagging? Can you answer this simple question? Which of these quantity is leading in terms of phase I am talking, and which is lagging? Can anyone answer? I is leading. JNVPTA is saying I is leading. How you recognize this part? The maximum of current reaches earlier as compared to the maximum of voltage. You can see this is T1, this is T2, and maximum of current reaches first. Or current reaches maximum value first, so current is leading. So you can write it as I leads voltage. Clear? The one thing that we learned in the previous class. The next thing, there were two more circuits. I hope we have studied. We have studied the purely resistive circuit and purely inductive circuit. So resistor only circuit. What was the conclusion? Conclusion was current and EMF are in same phase. That means they reaches their maximum value simultaneously. Current can be written as I naught is equals to E naught by R. In the same way, if I write about purely inductive circuit or L only circuit, where L is the inductor or the self inductance of the inductor. So what is the conclusion? Anyone remembers who leads in this purely inductive circuit and by what angle? JNV Ranga Reddy has joined. Amisha has joined. Okay, so I'm asking in the purely inductive circuit or L only circuit, who leads current or EMF? Who leads, current or EMF? Can anyone answer? I lags and V leads. Very good, JNVPTA. So in purely inductive circuit, EMF leads I by what angle? I hope you remember by pi by 2 angle. And the phasor diagram, you have seen that if this is Y and X axis, this is your potential EMF and current lags it by some angle 90 degree. This was 90 degree. JNV own goal is also here. So these were the things. And one more thing that you have studied in this previous class, what was that? That I naught is equals to E naught by XL. Do you remember what is the name of this XL? What we call it? What we call this XL? And what is its unit? Everyone should reply. Inductive reactance. Very good. Very good, JNVPT. Inductive reactance. And what is its unit? Ohm. Very good. Very good. One more thing. The formula for XL was omega L. Okay, JNV on goal. Henry is the unit of L. This L has a unit of Henry. The inductance has the unit of Henry, but the reactance XL is called inductive reactance and it has a unit of ohm. Clear? And the formula for XL is omega L, where omega is the angular frequency of the source. Clear? Now, one more thing that you can see here. What is the graph between XL and omega? If I draw a graph between XL and omega, this is reactance, this is omega. And if you draw the graph between these two quantities, line, you see that XL is directly to omega, so this is going to be a straight line, and this is a straight line. So try to remember graph. Don't need to remember. Lokesh has done. This is the graph of XL versus omega. Or these are the things that we need. Now moving towards the circuit, capacitive circuit. Capacitive circuit say the punchline, the first line. Okay, okay. Give me this. Give me this friends. Okay, am I audible now? Just confirm once. Am I audible now? Okay, thank you. Thanks, Vacha. Okay. So, first of all, we will discuss the punchlines. In purely capacitive circuit, what happens? Current leads the EMF by what angle? Pi by 2. One important thing. Now, if current leads the EMF by pi by 2 and we have applied some potential, so now the equation of current will be what? You can see the equation of EMF mentioned. What will be the equation of current then? The equation of current will be I is equals to I naught sine omega t. Now, anyone can answer what is the sign going to be? Plus or minus? Which sign I need to use here between omega t and pi by 2? JNVPTA is saying plus. Very good. Current is leading the EMF. EMF has the phase of omega t. Current has a EMF or current has a phase which is leading by pi by 2 is it will be plus pi by 2. So this is the equation of current. Now one more thing. One more thing. The next punchline I will say how you write the current. The maximum current in the circuit will be E naught by resistance. E naught by the resistance according to the Ohm's law. Now resistance of the capacitive circuit or the capacitance is denoted by XC, where XC is known as the capacitive reactance. XC is known as the capacitive reactance. So you can name it here. XC is capacitive reactance. Another thing, its unit is again ohm. Another thing, what is the formula for XC? XC is equals to 1 by omega into C. That means capacitive reactance is reciprocal to omega. Now, as we see this equation or this relation, first of all, you need to make a box out of it. Naina, you are late, I hope. Now, one more thing, which is very important. All these factors are here. Now we can draw the phasor diagrams, waveforms that will be on the next slide. What is more important here? A very famous question that everyone can answer. I hope you all can answer the question. Question is capacitor blocks DC. Why? You need to answer why it blocks DC. Joel has joined. Infinite resistance. Very good. Pooja has also joined. Okay. Now listen to me. Capacitor blocks DC. Now can you see that XC is the resistance and it is reciprocal to omega. Now if I talk about for DC, what is the frequency? Frequency is zero. DC is continuous supply. It doesn't change with the time or doesn't change periodically. So frequency is zero. So what I say, capacitive reactance is will be 1 upon omega is what? 2 pi F into C. So if F is zero, X cap in inductive, sorry, capacitive reactance tends to zero. Sorry, tends to infinite. And if capacitive reactance tends to infinite, that means it offers infinite resistance. It offers infinite resistance to the flow of the charge. That's why we generally say capacitor blocks DC. Clear? Now, what will be the graph of XC versus omega? Can anyone answer? Next punchline is what will be the graph of XC versus omega? Here, if I say this is XC versus omega graph, XC versus omega graph. Can you see that XC is reciprocal to omega? So the graph will be something like that. It will go start from infinity to infinity. It will be something like that. This is the graph of XC versus omega. Audio is again breaking. Okay, I need to find a solution for that very soon from the next class. From the very next class, I hope we will be having some solution of that. Okay. Right now, I think all these things are clear in your mind. Who leads? What is the current? What is XC? What is the formula for XC? What is the graph? Capacitor blocks DC. All these things are clear. Now moving further. How we can draw the waveforms? Like here, the red one is voltage, which is starting from the origin, and this is current, which is leading by what? Pi by 2. On the same note, this is the graph. This is omega t. This is phasor diagram. This is omega t. Anti-clockwise, we always take the angles anti-clockwise direction. Now, current leads it. That means this angle is again going to be pi by 2. These all are the things. Now we will solve one question and after that we will move towards another circuit. Hope you can solve the question, which is on the next screen. Am I audible to everyone? Is my voice still breaking? Uh, Joel. Okay, I am audible. Okay, very good. So there is a question on the screen. I will give you some, just a calculation. So I will give you 35 seconds or 40 seconds you can take and try to solve it out. Now, in the meantime, I will try to read out the names of the students. Hemant, PTA, Lokesh, Ongol, Bhaskar, Namit, Spandan, VK, uh, Amisha, Akhil, Kumar is also here. Kumar, you are not answering today. Nandan and a few more students are also here. Anyone getting the answer? According to the question, a 40 microfarad capacitor, this is a capacitor, is connected to a 200 volt 50 hertz supply. 200 volt 50 hertz. As soon as I see the frequency, I can recognize that this is the AC. So this is 200 volt and 50 hertz AC. The RMS value of the current. So RMS value of the current they are asking. So what is, how you can write the current? You can say IRMS is equals to, okay, first of all, just apply the Ohm's law. What is Ohm's law? I is equals to E by R. Resistance of the capacitor is what? XC. Clear? Now they are asking the RMS current. So if I use RMS here, then I need to use RMS here as well. Now just put the values and you will get the answer. Now for the time being, what is ERMS? I told you yesterday, whenever there is a supply given, then this value is nothing but the RMS value. So this is RMS value. RMS value is directly given as 200 volt. XC is what? 1 upon omega C. 1 upon omega C. This omega C can be transferred in the numerator. So how you can write IRMS is equals to omega can be transferred, omega C can be transferred, that is 2 pi F into C into 200. Clear? Now put the values. 2 pi is 3.14, F is what? 50 hertz. Capacitance is what? Joel is saying 2.5. Okay. Capacitance is what? 40 microfarad, and this is 200. Now this is just the calculation. Can one or two more persons can calculate and confirm the answer of the Joel? Joel is saying of 2.5 ampere. Okay. 2 fives are 10. This is going to be 100. 2.5. JNVPT is also saying 2.5. Okay, so this is just the calculation. I am assuming your calculation part is good. So this is 2.5 ampere, which is option number C. Clear? Moving further. LR circuit. Now we will focus on one combination of circuit in which we will deal with the combination of the L and R. After that, there is another combination. There can be another combination like LC circuit, like CR circuit, but we will not go with that. You need to learn it here. After that, we will directly move towards LCR circuit, LCR series circuit. We will directly move towards that. So be focused, be alert in this circuit. Look at that. This is L and R circuit connected in series. Now, when you apply the AC supply across it, some potential. First of all, one thing that is very much you can understand, these two L and R are connected in series. If they are in series, the current will be same in both of them. Let's suppose current is I, and current will remain same in both because both are connected in series. Now, another thing I'm saying, the potential across inductor, let's suppose, is V1, or you can say it is VL. L indicates that it is across inductor. And let's suppose potential across resistor is VR. Now current is same in both these resistor and inductor. Now first step, we will draw a phasor diagram. Like how you can draw the phasor diagram? For phasor diagram, first of all, look at the quantity which is constant out of EMF and current. So current is constant. So what I did, I take two reference axes like your X and Y. And after taking two reference axes, on one of the axes, I have taken current. Because current is constant, so I have taken current along the x-axis. You can choose. I have taken current along the x-axis. Now, you need to remember that potential across inductor, potential across inductor leads the current by 90 degree. That means this is going to be our potential across inductor, that is VL. Clear? And potential across resistor is in same phase with the current. That means this is going to be potential across inductor. This is going to be potential across inductor, that is VR. Now can you see that VL and VR? This is our phasor diagram. And can you again see that the sum of these two quantities VL and VR is going to be our net EMF which I have applied, or you can write it as, here we have taken VL and VR as vectors, as anti-clockwise rotating vectors. So these are vectors. So what I'm saying, the net EMF is going to be the vector sum of VL plus VR. Try to remember, it is not the algebraic sum, it is vector sum of VL and VR. In our consideration, our conventions, I'm talking about. Okay. If you deal with VL and VR, if you add VL and VR, the resultant will be somewhere here, and resultant will something look like that. This is our resultant, which will give our net EMF that is being applied. So this net EMF will be what? Can you use parallelogram law, that is root of VL square plus VR square. Now, if you look at here again, E is equals to, from Ohm's law. Ohm's law, if you apply, current is I, V is equals to what? IR. V is equals to what? I into resistance. So I and resistance of inductor is what? XL, that is squared, plus IR squared. You can take out I square, and after root it will be I root of XL square R square. This is EMF. Let it be equation number first. Now, after calculating these two things or the net EMF, the important thing is that, look at me. Now look at me. In the current electricity chapter or in the capacitor chapter, you have seen the equivalent capacitance, the equivalent resistance term. I hope you have seen that term. The series combination, the parallel combination, and you have solved it for the equivalent resistance and capacitance till now. Now, what I'm saying, when these two quantities, one is inductor, one is resistor, is connected, they will also, the combination of these two will also try to oppose the current. Now, this combination, we will calculate the effective resistance of this combination. We will try to calculate the effective resistance of this combination, but we will not name it as effective resistance, we will name it as impedance. So the name given to this effective resistance is impedance. I think the definition of impedance is clear to everyone. What is impedance? Impedance is the effective resistance of a series AC circuit, or the effective resistance of the AC circuit. Okay. Now, one more thing. What you do, like this is the circuit. If you make a effective circuit or equivalent circuit, I don't know whether it will behave more like an inductor, more like a resistor. So I have drawn the effective part as a box. The applied EMF is E here, which is AC. And the combination of these two will have some resistance, some effective resistance, which is known as impedance, denoted by Z. So this is the equivalent circuit of this one. This is what? Equivalent circuit. Now, what is Z? Z is known as impedance. What is the definition of impedance? I hope it is clear with everyone. Now, it will supply the same current as supplied here, I. So, for equivalent circuit, for equivalent circuit, if you apply Ohm's law, what you will say, EMF is equals to I into Z. Now, if you compare these 1 and 2 equations, you will get impedance. So Z is equals to what? Root of XL square plus R square. This is the result of impedance that you should always remember. For the LR series circuit, what is impedance? XL square plus R square. Is there any doubt till now that what is impedance? Okay. This statement must be clear, because there might be a question. There might be a question in which this value will be given as 20 volt and this value will be given as 40 volt. And they will ask you what is the net EMF, what is the EMF supplied. Or sometimes it will be like this is given as 100 volt, this is given as 20 volt, and they will ask the potential across the resistor. So some of the students made a mistake, like this is total 100, this is 20, so this must be 80, so this will be wrong. This is not going to be 80. You need to calculate using the vector addition like this. So you need to follow this thing. Now, one more thing that we did previously, what we did one more thing, that what is the phase angle between EMF and current? What is the phase angle between EMF and current? You can see here, this EMF and current are something like that. This angle, let's suppose, is phi. So can anyone answer who is leading? This is EMF and this is current. Who is leading according to you? Who is leading in this circuit? EMF is leading. Very good. EMF is leading. By what angle it is leading? So I can calculate the angle. You can calculate, you can also calculate tan phi is equals to perpendicular over base, that is VL over VR. Or you can simply write it as tan phi is equals to VL is what? IXL. VR is what? IR. This is just Ohm's law. I and I can be cancelled. Tan phi is equals to XL over R. So what is the ultimate conclusion in LR circuit? EMF leads the current. Not by 90 degree, but by what angle? By angle phi, where phi is what? XL over R, or tan phi is equals to XL over R. I hope it is clear. Moving further. Okay, so there is a question. Just try to solve the question. You have some 40 seconds. Everyone should solve at least. If you don't know, I will give you a reminder that tomorrow 3 p.m. Yes, tomorrow 3 p.m. On this time, there is a class that is known as weekend class. In this class, we are going to discuss the questions of EMI chapter. The previous year questions of EMI chapter we will discuss in tomorrow's class. So try to join that class, and day after tomorrow on Sunday uh, at 11 a.m. we will be discussing the questions, previous year questions of this AC chapter. So for these two classes, everyone should be present there, because in this weekday classes we have completed the theory part, or we are completing the theory part. So in the weekend class we will be covering the questions, question and answers, or the previous year questions. So for that, be on time, because we will just discussing question answers. Anyone got the answer? Okay, listen to me. Listen to me. Look at that. Look at it, the screen. First thing, 3 ohm. Namita is saying 3 ohm. Okay, very good, Namita. First of all, everyone should listen to me. Just try to focus. When a 10-volt DC is applied across a coil, when they are saying coil, like they are saying the type of coil is inductor type of coil, current through it is 2.5 ampere. Now, as soon as I see That current is only 2.5 ampere when I am applying 10-volt DC. Like if you come, look at that. Suppose I will delete this diagram. Suppose this is inductor and it has some inductive reactance XL, you know. Now, if it has some XL, this XL is what? Omega L. If you apply DC to it, if you apply DC to it, the frequency of DC is zero. That means XL will become zero for DC. For DC, the effective resistance is zero. That means current should not have the value of 2.5 ampere only. It should be another level, should be maximum, or it should be infinite. It should be not be defined in that situation. That means this coil, this inductor coil is not ideal. It is having some resistance. And if an inductor coil has some resistance, then this is not the case of purely inductive circuit. This is the question which involves LR circuit. Is this statement clear to everyone? What I'm saying? They are applying DC to it, and this is the case of LR circuit. How I recognize this thing, is this part clear to everyone? If you want me to repeat, you can ask me. Otherwise, I have explained it. Now, they are saying 10-volt DC is applied. Clear? And current is 2.5 ampere. Now, how you can write the current? I is equals to E by resistance. Now you can see resistance of this inductor part is zero, but this resistor has some resistance R. So I is equals to E by R. Current is given as something, how much current is given as 2.5 ampere is equals to EMF is 10-volt divided by R. So you can calculate resistance. Resistance is coming out to be 2.5 forza. Resistance is coming out to be 4 ohm. So in this LR circuit, this resistor has a 4 ohm resistance. Now they are saying if 10-volt 50 hertz AC is applied, the current reduces to 2 ampere. Now again, I am going to apply AC. I will redraw the circuit. Again, similar L, R, but the supply has AC. How much? 10-volt 50 hertz supply. So the current has reduced to 2 ampere only. So if in this case, or in this LR circuit, if you write the current, everyone should be focusing how you write the current. I is equals to again E by, this time not resistance, this time it is going to be impedance. And what is the impedance? Root of, anyone remembers the formula of impedance for the LR circuit? We have driven it in the previous slide. That is XL square plus R square. Clear? Reactance is what XL they are asking to calculate. Now coming. If you can transfer, it will become XL square plus R square is equals to E over I. Is it clear? Now EMF is 10-volt, current is 2 ampere. So you can say it is going to be 5. 2 5s are 10. This is just the calculation now. If I transfer this square root, so it will become XL square. What is the value of resistance? Is 4 ohm. 4 ohm means 16 is equals to 25. I have transferred square root, it will become square. So XL will be what? Or XL square will be what? 9. XL will be 3 ohm. Someone has answered, that was correct. I just forgot the name. One person has answered 3 ohm. Very good. Very good. Who was that person? Uh, Namita. Very good, Namita. Okay. So this is 3 ohm. Is the question clear to everyone? Because everyone should learn the same. This is a very famous question in the NEET exam and from the last few years. This simple type of question is coming in the JEE mains exam as well. So I hope everyone is getting the questions. Moving further. Now there is LCR series circuit. This is again the important part and the resonance circuit is also based on it. So first of all, we will discuss, we will draw the diagram of the LCR circuit. This is LCR circuit, if you can see. Again, the same thing, this is connected in series. And if it is in series, then one thing will be same for all, that is current. Potential across it is VL. This is going to be VC. This is going to be VR. Clear? Now the next statement, what we will do, we will draw the phasor diagram. For the phasor diagram, I told you, first of all, draw the axis, X and Y axis. So this is my X and Y axis. Clear? Now, second thing, which is constant throughout the circuit, that is current. I will draw current here. This is current I. Now you know potential across inductor leads the current by 90 degree. So this is going to be potential across the inductor, VL. Potential across capacitor lags the current. I hope you remember this thing, na? This is the potential across inductor which lags the current by 90 degree. This is VC. And this is potential across resistor. What it will do? It will be in the same phase with the current. This is VR. Now you have three vectors and the vector sum of these three quantities will give you what? Will give you total applied EMF. So if I do, or if I write the statement, total net EMF is equals to vector sum of VL plus VC plus VR. And if you solve this thing, three vectors, the equivalent of three vectors, you can see that VL and VC are opposite in direction. So the resultant of these two will be something like that. If I draw the equivalent circuit, uh, it will be something. This is our VR, this is our I, and VL and VC are opposite to each other. So it can be like this one, VL minus VC. If two vectors are opposite to each other, they can be subtracted. Like, I hope you know this thing. So this is the case. Now, what will be the net EMF? This is going to be the net EMF at some angle, let's suppose phi, with the current. Now, you can write this EMF E as root of the parallelogram law, VL minus VC whole square plus VR square. Again, if you simplify it, you can take I outside. And if you take I outside, it will be XL minus XC square plus R square. Out of this, if you remember the comparison from the last circuit, that is LR circuit, we have drawn some equivalent of this circuit. So Z is coming out to be, this portion is nothing but Z. So Z is what? Root of XL minus XC square plus R square. Students, tell me the name of the Z. What is Z? What is Z? What? 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 Is Z? Impedance. Very good. Very good, Santosh. Impedance. So this is the formula for Z. Very good, Joel. Namita. Very good. Everyone is present. JNV on goal is also here. Okay, so this is Z impedance. Now one more thing. Who is leading? According to this diagram, what I have assumed, you can notice that I have assumed that VL is greater than VC. That's why EMF is coming in the upward direction. What if VL is less than VC? So we will do these cases. So before that, we will just write the formula of tan phi. Tan phi is what? VL minus VC by VR. Or you can say tan phi is equals to XL minus XC by R. You can cancel out I throughout the equation. This is tan phi. XL minus XC divided by R. So two important things. One is impedance. Now from LCR circuit, you can form any of the circuit, any of the impedance for any of the circuit. Like if I say, if the circuit is CR circuit, if the circuit is CR, that means XL is going to be zero. Are you getting my point? From this impedance of LCR series circuit, you can form impedance for any of the circuits. Like if I say CR circuit, can anyone tell me what will be the impedance of CR circuit? Using this formula, can you get the answer for CR circuit? It will be difficult for you to write, but I can understand your feelings. If you say yes, sir, with some loud voice, if you can say yes, sir, if you can type yes, sir, with some loud noise, I can understand that you are getting the answer. For CR circuit, can you write the impedance? For CR circuit, inductor is not there. Root of XC square plus R square. Very good. PTA is saying, JNV PTA is saying, root of XC square plus R square. Very good. Clear. Z is equals to root of XC square plus R square. Very good. Now, one more important thing that we will discuss here for the LCR circuit. Look at that. We got the formula of tan phi. Tan phi is equals to XL minus XC by R. Clear? Now, first case, if I discuss here, if XL is greater than XC, then can you see that tan phi is positive? Can you see that tan phi is positive, or you can say phi is positive? Phi is positive means diagram that you have drawn is correct. This is I, this is VL minus VC, and this is net EMF, and this is phi. That means EMF leads the current. EMF leads the current. EMF leads current. And circuit is more inductive. If EMF is leading, that means circuit is more inductive. Now, in the second case, if I talk, if XL is less than XC, then what is the ultimate conclusion? Can anyone say? XL is less than XC. Then ultimate conclusion, you can draw all these things. What is the ultimate conclusion? EMF lags the current. How? Because tan phi will be negative or phi will be negative. And if phi is negative, then you can draw the phasor diagram. Negative phi means if this is current, then this is the phi. Negative phi means EMF lags the current. And if EMF lags the current, circuit is more capacitive. Circuit is more capacitive. And final case, I hope everybody remember can understand what will be the final case. If XL is equals to XC, can you tell me what will happen in this case? If XL is equals to XC, phi will be what? Phi will be what? 0. And circuit will be resistive. Very good. And circuit will be resistive. I will say circuit will be resistive. Now, one important thing in this whole scenario, what you can understand that when XL and XC, that means inductive reactance and capacitive reactance, both becomes equal, circuit behaves as resistive circuit only. And this is going to be the condition for resonance. After this, we will study about resonance. So this is the condition of resonance as well. Okay, one more thing that I will discuss. For that, you need to be very much focused here. I will try to draw, my aim is to draw the graph of current versus omega. I will try to draw the graph of current versus omega, like how current varies with omega. Before drawing that graph, I will draw another graph of Z versus omega for LCR circuit. What is Z? You can see the formula of Z. What is the formula for Z? Z is equals to root of XL minus XC square plus R square. Clear? Now we will try to draw the graph of Z versus omega, how it varies with omega. Now for the variation with omega, what you need to do, just check the variation of XL and XC with omega. So if I check with that, these graphs are very important. These graphs are very important. So be alert. This is omega. And on the y-axis, I am taking XL and XC both. Look at that. You can see XL was something like that. We have drawn this graph already. And for XC, we have also drawn the same graph like this one. Or I can simply draw it again. This was the graph for XC. Green one is for XC, yellow one is for XL. Now, can you see the difference? The frequency at which these two quantities become equal, these XL and XC becomes equal, is known as natural frequency or the resonance frequency denoted by omega naught. So you can remember this is known as omega naught frequency at which XL and XC are equal. This frequency is denoted by omega naught. Notice this point. Now, starting from 0, can you see that this difference of XL and XC is decreasing? This difference of XL and XC is decreasing until omega naught. That means XL and XC, this difference is decreasing. That means impedance is also decreasing. Up to what point? Up to omega naught. That means impedance was decreasing. What's happening? What was that? And it was decreasing, decreasing, decreasing. What I'm saying, after this omega naught, it starts increasing. Can you say that? It starts increasing. And if it starts increasing, I will draw it again like that. It starts increasing. So the point at which it becomes minimum is omega naught. Can anyone tell me what is the value of Z at this point? What is the value of Z at this point? What will be the value at this point? Can anyone answer? Any one student can answer. Very good. JNVPTA and Hoysala says R. Very good. This value is going to be R. Now, if impedance is varying this way, when impedance is decreasing, current will be increasing. So you can draw it something like that. And the maximum current will be at what point? Omega naught. So I have drawn three graphs, one for Z versus omega, one for I versus omega, and one for XL versus omega or XC versus omega. Is everything is clear in your mind? It should be crystal clear in your mind. And this graph is going to be used for the resonance purpose when we study about selectivity and sharpness of the circuit. And after that, two topics are remaining. One is, I will say, power in the AC circuit. And after that, one more topic is there, that is transformer, I think. So after the completion of these two topics, we will be ending tomorrow. Akhil, what you want to say? So how many of you are joining the class tomorrow for the question answer session on EMI? JNV on goal, PTA? Very good. Amisha, only five. Raju, very good. Devdutt, Manikanta, Navya, okay. Nandan, okay. So on this note, everyone is joining, I hope. So we are ending the session. Bye, everyone. Should I end the session now? Okay. Bye, everyone. Thank you, Bacha. Thank you, Joel. Thank you, PTA. Thank you, Amisha. And everyone should answer in the class. Like in tomorrow's class, everyone should answer, whether it's wrong or right. Thank you, Shekha. JNV own goal. Who is mad?